Section 15.5 Arithmetic Series. Okay, so first off, let me characterize a series. So a series, 5, 8, 11. So suppose we had a sequence 5, 8, 11, 14. And what we did is we just kept adding. Uh, then this would be called a series. And so a series is just a whole bunch of numbers that we add up. So we can think of this as follows. I can characterize a series as, well, you have the nth term is just equal to the previous term plus some number. And this number could be, well, it doesn't have to be a constant, it could be anything. And so we can think of this as being uh, every term if, so a series is a sequence. Oops, sorry. Oops, hit the wrong one. Yeah, well, right. It's just a particular type of sequence. So it's a sequence in which each term is found by adding, and it could be, well, adding or subtracting. And so a sequence is just a series is really just another way to say a sequence. Okay, it's just that, well, I keep adding something. So I'll give you what's called an arithmetic sequence. Suppose you have the following arithmetic sequence. Oh, let's say um, 1, 4, 7, 10, 13, etc. Then the corresponding arithmetic series is just 1 plus 4 plus 7 plus 10 plus 13. So in an arithmetic series, each of the terms that you're adding to get to the next term in your series is just the term in your arithmetic sequence. Y- yes, but that's the next section, which is geometric series. So you can also uh, multiply by something. So somehow your next term is something different. Uh, well, in a series, you're always adding. So in a series, it's always found by adding something. Okay. So if the thing that you start out with is your arithmetic sequence, then the corresponding series is called a arithmetic series. So let me give you some notation. the sigma notation. So sigma notation. So suppose I have here 1, 2, 6, 18, 54, etc. Let's just go up to 54. Okay. So notice that in this case, uh, each of these terms here, well, the next term that I'm adding is always going to be, say, 3 times what the previous one was. So there could be a way to simplify this. So can this be written uh, in more compact notation? And this will be called the sigma notation. So this symbol here is called sigma. It is, it denotes the sum. It's the summation. And so if I write, I haven't told you what it is yet. Actually, it's a Greek letter. It is the Greek letter sigma. Um, so if you ever go by like a college that has a fraternity or sorority or whatever, you'll see the Greek letter sigma. It's that Greek letter. It's the capital sigma in the Greek letter alphabet. And so suppose I write, oh maybe I'll write k. K equal 2 to 4 of 5k plus 1 or something. So this notation would mean what I would do is, well, this is called my dummy index. This is my initial value. And this is my, well, ending value. For my dummy index. So this would denote, well, I first replace my k here by the number 2. I then add to it, well, the next number after 2 is 3, and so I replace k by 3. And I keep doing that till I get to my the ending value of my index, which in this case is actually, I just did it for very few values, 4. Okay? And so let me actually do some examples. And so let's see, on page 664, let me do problem number 2. I have here the sum n equals 1 to 8 of 2n plus 3. In exercises 1 through 12, write the series in expanded form. And so, first I'm going to replace n by 1, by 2, by 3, by 4, by 5, by 6, by 7, by 8, and then I'm done because I first started replacing each of these n's by 1, and then keep going until I finish writing them once I get that n here is 8. And that is the sum of all, and so that is what this compact notation meant. And so the sum, n equal 1 to 8 of the expression 2n plus 3 is just this following sum. Let me do problem number, let's say 8. Sum k equaling 1 to 6, negative 2 to the k. And so let's replace k by 1, 2, 3, and keep doing this till I get k equaling 6. 4, 5, 6. Now that I've reached 6, I'm done. And so the sum, k equaling 1 to 6 of negative 2 to the k, just means this sum. Let me do problem number 12. Sum k equaling 1 to 4 of 1/2 to the k. So this is equal to 1/2 to the first, second, third, fourth. And that is what this notation means, this summation. Let me do problem number 14. So it says 3 plus 7 plus 11 plus 15 plus, and let's do this for the next, for all these values, and let's add up it so that we have 63 terms. If you notice here, in this series here, I keep adding up a whole bunch of terms, and each of these terms here seem to be, well, if I go from 3 to 7, 7 to 11, 11 to 15, what type of series is this? What type of sequence is this? Well, notice that this looks like an arithmetic sequence. Therefore, this is an arithmetic series. And so I know that for an arithmetic sequence, the general term to arithmetic sequence is just equal to a sub 1 plus n minus 1d. And so I know that I can characterize the nth term as, well, the first term is 3, The common ratio, well, notice I keep adding 4 to get to the next term. So let me multiply 4 inside the parentheses. And so using the distributive property, I have a sub n is equal to 3 plus 4n minus 4, which is equal to 4n minus 1. So I can say that this series above is just equal to, well, the sum so 3 plus 7 plus 11 plus 15 plus, this is just equal to the sum of, well, a sub n, where a sub n is 4n minus 1, where n is equal to, well, a, well, I'm counting from n equals 1, and there's 63 terms, so I'll do this for 63 of these. And that is a much more compact notation saying that, well, I'm adding up 63 of these terms, and each of these terms just look like, well, 4n minus 1, for n equaling 1 to 63. Let me do problem number 16, negative 10. So this is actually called a arithmetic series. So notice that I've characterized this arithmetic series. Okay. Negative 10. Actually, I should probably give it a different color so it doesn't look like I'm multiplying or something. Let's do it there. So this is the arithmetic series. Negative 10, negative 5, 0, 5. I'm going to be adding up 120 terms. So a lot of terms here. Okay, so let's do this. So if I notice, again, I seem to be adding the same amount. So this is a arithmetic series. And so if I look at the arithmetic sequence from which it was formed, I have here a sub n. Well, I should say, so it's arithmetic sequence, arithmetic sequence. So this series is formed from an arithmetic sequence. So it's an arithmetic series where a sub n is equal to, well, a1 plus n minus 1d. That is the general term for an arithmetic sequence. And so in this case, the very first term, a sub 1, is negative 10. The common ratio, well, I keep adding 5 to get to the next term. The common ratio is 5. So let me multiply the 5 inside the parentheses. So using the distributive property, I get a sub n is equal to negative 10 plus 5n minus 5. And so 5n minus 15. So therefore, my arithmetic series can be written more compactly as the sum. In this case, well, again, we're counting starting at 1. So n equals 1. And we want 120 terms. So it goes up to 120. And, well, each term is characterized by the following formula. It is just 5n minus 15. And that is how I write this in a more compact form. Let me do problem 18. 18, 6, 2, 2/3, 2 over 729. Okay, so in this case, notice that I keep dividing by 3 to get the next term. So this is actually a geometric series, a geometric sequence. So this is formed from a geometric sequence. So again, this was a arithmetic series. In this case, since it's formed from a geometric sequence, we'll actually call it a geometric series. So I know that from the last section, I can characterize the general term to arithmetic sequence as an, a1 equaling a1 r to the n minus 1. So the nth term is just the first term, 18. Well, to go from 18 to 6 to 2 to 2/3, I get to multiply by 1/3. Okay, so that's all nice and fine. But the problem is they didn't tell me how many terms I have. So I have to actually figure out the number of terms in this series. And so let's figure out how many terms. So, but you know, how many terms? Okay. So I don't know how many terms I'm adding. And so let's look at the last term. The nth term. And so I know that the last term here is equal to 2 over 729. Okay, so let me multiply both sides of my equation by 1 over 18. Divide both sides of my equation by 18. And so if I do that, I get, oh, this is very similar to what we did actually just a few minutes ago. So let's multiply by 1 over 18. Dividing by 18 is the same as multiplying by its reciprocal, 1 over 18. Now, 18 divided by 2 is 9. 9 times 729 is 6561. Okay, so let's try to solve that. So let's take ln of both sides of my equation. And so I get ln 1 over 6561 equals, well, I can, by the properties of logarithms, I can bring down the exponent out in front. Multiply ln 1/3 inside the parentheses. So I get ln 1 over 6561 equals n ln 1/3 minus ln 1/3. And so subtract or add ln 1/3 to both sides of my equation. And so I get ln 1 over 6561 plus ln 1/3 equals n ln 1/3. Divide both sides of my equation by ln 1/3. And so I get n is equal to ln 1 over 6561 plus ln 1 over 3 divided by ln 1 over 3. Plug that into your calculator. I think you get 9. So we did this before, and we actually got well. We did, except everything was it was everything was the negative of this. We did it with ln of 65, 61 plus ln of 3 over divided by ln of 3. We got 9, so obviously we get the same thing here. So there are 9 terms. So now I can characterize this. So 18 plus 6 plus 2 plus 2/3 plus 2/9 plus 2 over 729 is just equal to sum. N equals 1 to 9 of, this was what, 18 to the 1/3 n. 18 to the 1/3 n minus 1. And that is your answer. So you can write this sum more compactly in that form. Okay, so in this case, since each of these are, well, found by adding a whole bunch of terms that are part of a geometric sequence, then this is called a geometric series. So this actually was a geometric series that we're looking at. Okay, so let me do problem number 20. 2, 6, 12, 20. In exercises 19 through 24, identify whether the series is arithmetic or not. So I have to see, do I add always the same amount to get to the next term in this sequence from which this series was formed? Well, 2 plus 4 gives me 6, plus 4 gives me 10, not 12. So this is not arithmetic. So not arithmetic series. 22, 3, 5, 7, 9, 11, etc. And so 3, to go from 3 to 5, I have to add 2. 3 plus 2 is 5, plus 2, 7, plus 2, 9, plus 2, 11. Oh, that does look like an arithmetic series. So yes, this is an arithmetic series. So yes, this is an arithmetic series. 24. 1 squared, 2 squared, 3 squared, etc. Well, to go from 1 to 4 to 9, well, let's see, 1 plus 3 is 4, plus 3 is 7, not 9. So no, this is not arithmetic series. So not arithmetic series. This has a form, so there's actually a name for this. This is a Riemann zeta function, well, series. Okay. So this is actually a very, very famous series. There's something that related to it called the well, we run hypothesis, which is stating that if you find the zeros to this uh, series, then they must all lie along the complex plane with real part equaling negative one half. And if you're able to prove that, they'll give you like $1 million. The Clay Institute will give you $1 million. No one's been able to prove it. It's a long-standing, 100-year-old problem. It's no one's really got close to solving it yet. Okay, so let's do problem 26. But before I do that, I guess I should uh, derive something. Um, and so the sum of the first n terms of an arithmetic series. So before I tell you that, I guess I'll give you a little story. So Carl Friedrich Gauss, when he was 9 years old, he was given the following problem. So his instructor was, I guess, overwhelmed by having all these children ask questions. And so he decided to put a problem up on the board that would take them forever to do. So he said, well, add up the following numbers 1 plus 2 plus 3 plus dot dot dot, all the way up to 100, and do that, So he's expecting that, well, it'll take them at least the whole day to do this, and he'll be able to sit there and, not be bothered by these children. And well, immediately after he wrote down this, Carl jumped up in his seat and said, 5,050. And so they knew that, well, this person must be of extraordinary character, mathematical character. And he went on later to, well, over the weekend, basically prove everything that we're doing here. And then later to prove some very, very famous theorems. So let's see how he did it. So suppose let S equal 1 plus 2 plus 3 plus. So let's go into the mind of a 9-year-old. And so let's write this. Instead of going from 1 to 100, let's go from 100 and go down to 1. So let's reverse this series. And now let's add these together. Well, S plus S is 2S, whatever the sum is. And well, 1 plus 100 is 101. 2 plus 99 is 101. 3 plus 98 is 101. Matter of fact, if you keep adding up all these, you always get 101. And there are 1, 2, 3, 4, there are 100 terms here. And so this is equal to 10,100. So if I divide both sides of my equation by 2, I get that S is equal to 5,050. And so that's how Carl Friedrich Gauss figured this out in his head in, 5 seconds or whatever. He just said, oh, well, they always add up to 101. There are going to be actually 50 of those. And you add them up. So multiply 50 times 101, you get 5,050. Okay. You can do that in general. And so it turns out that if you do that in general, I have that, so the sum. So suppose you have, oh, maybe I'll call it K. Suppose you have a arithmetic series, and you add up, oops, and let's call this K, and you add up the first n elements of those. Well, then you'll just get that this is equal to, let me move this over slightly. So this will equal n over 2 times an, a1 plus an. And well, actually, a lot of times we give as a notation for this, rather than writing this all out, I'll just call it S sub n. So that's the sum of the first n terms of an arithmetic series. So a lot of times we just write this formula as n over 2 a1 plus an. And well, I also know that a sub 1, a sub n, is equal to a1 plus k minus 1 plus a1 plus n minus 1 times d. So I can also write this as follows. Well, a1 plus a1 is 2a1 plus n minus 1d. So I can write either formula, and that is the sum of the first n terms for a arithmetic series. So let's, and of course you can prove this by induction. Let me do problem number, let's say 26. -5 plus -3 plus -1 plus 1 plus 3. Let's add these all up. And so I know that the sum of the first n terms of an arithmetic series and so this is just n over 2. I can either use a1 plus an or the second thing. Well, since I don't know the last one, I can just use the second formula, because in this case I know both how many terms there are. I know the first term and the common ratio, and a common difference. And so this is 2a1 plus n minus 1d. And so I want to add up the first 100 terms. And so, again, it says in exercise 25 through 30, find the sum of the first 100 terms of the arithmetic series whose first few terms are given. So I want to add up the first 100 terms. So 100 over 2. 2 times a sub 1, well, the first term is -5. I'm adding up 100 terms, so n is 100. The common difference is, well, In order to go from -5 to -3 to -1 to 1 to 3, etc., I keep adding 2. The common ratio is 2. Yep, 2. Okay. Oh, that looks like a Z. 2. And so let's simplify this. So that's going to be 100 divided by 2 is 50. Negative 5 times -2 is -10. 100 minus 1 is 99 times 2. And so I get 50 times, that's 198. And so 188 times 50 is 99,900. Okay. Oh, no, it's not. It's 9,800. It's at 88, not 90. It's 88. It's got to be 9,500 less, 400. 9,400. Okay. And so if you add up all these terms, you add up 100 of these terms, you get 9,400. Let me do problem number 28. Well, we know what this is. 1 plus 2 plus 3 plus 4 plus. Let's add up the first 100 terms of those. Well, again, the sum of the first 100 terms for arithmetic series is just n over 2 times 2a1 plus n minus 1d. And so the sum of the first 100 terms is just n, 100 over 2. 2 times, well, the first term is 1. I'm doing 100 terms, so it's 100 minus 1. The common ratio, common difference is 1. I keep adding 1 to get to the next term. And so this is 50. 2 plus, well, 99 times 1 is 99. So it's 50 times 101. That should look very familiar. The 50 times 101, which is 5,050. We got what Carl got when he was 9 years old. So we're as good as a 9-year-old now. Let's do problem number 30. 8, 3, 2, 7, 12, etc. And so let's add up the first 100 terms. Notice that we keep adding the same amount, -5, to get the next term. So this is an arithmetic series. So since this is an arithmetic series, I can use the following formula. And so let's add up the first 100 terms. First term is 8. I'm adding up 100 of these terms. In order to determine the common difference, well, notice that I keep subtracting 5 to get to the next term in my sequence. So my common difference is -5. Let me simplify this. So this is equal to 50 times 2 times 8 is 16. 100 minus 1 is 99 times negative 5. And so 99 times negative 5 is 495. And so you get 50 times a negative 479. And so you get a negative 23,950. So if you add up the first 100 terms of this arithmetic series, you get negative 23,950. And that's your answer. Let me do problem number 32. Negative 3, 0, 3, 6, etc. In exercises, wait. I wrote down the wrong thing. Problem 32. Negative 1, 3, 7, 11, 151. In exercises 31 through 33, find the sum of the arithmetic series. Okay, so I know that this is an arithmetic series, so the sum of the first n terms of arithmetic series is just n over 2 times a1 plus an. I know the last term, and so that's going to be 151. I know the first term. Unfortunately, I don't know n, so I've got to figure out what n is. So I'm going to use the fact that the general term to an arithmetic sequence is given as follows. And so let's look at the last term, the nth term. And so the last term is 151. The first term was negative 1. I don't know what n is, but whatever n is, that will give me how many terms in this sequence. And so to go from negative 1 to 3 to 7 to 11, I have to keep adding 4. So the common difference is 4. Let me multiply 4 inside the parentheses. So 151 is equal to negative 1 plus 4n minus 4. So 151 is equal to 4n minus 5. Add 5 to both sides of your equation. So 156 is equal to 4n. Divide by 4. So n is equal to, oops, was it? I believe 39. So 156 divided by 4 is 39. So now I can figure this out. So I want to add up the first 39 terms. So this is equal to 39 divided by 2 times, well, a sub 1 is negative 1. A sub n is 151. And so this is equal to 39 over 2 times 150. And so 39 times 75 is 2,925. So if you add up all these terms, you get 2,925. 34. 34. 1, 3, 5. Oh, this is a nice one. In exercises 34 through 36, find a formula for the sum of the first n terms of the arithmetic series whose first few terms are given. And so, hopefully some of you people have noticed this uh, characterization. So I know that S of n is equal to n over 2 times 2a1 plus n minus 1d. So let's add up the first n odd numbers. So it's just n over 2. Well, the first number in the sequence is 2. The common difference in this sequence of numbers, 1, 3, 5, 7. Well, I always have to add 2 to get to the next term in the sequence. So 1 plus 2, 3, plus 2, 5, plus 2, 7. So the common difference is 2. Let me multiply by 2. And so I get S of n is equal to n over 2 times 2 plus 2n minus 2. The 2's cancel. So you get S of n is equal to n over 2 times 2n. The 2's cancel. So you get n squared. So that means that 1 plus 3 plus 5 plus 7 plus adding up the first n terms is just equal to n squared. So if you add, well, 1 is 1 squared. So the square of 1 is 1 squared. And then 1 plus 3 is 4, 2 squared. Plus 5 is 9, 3 squared. Plus 7, 16, 4 squared. Plus 9, etc. So you just keep adding them up, and you keep getting the next square term. So if you add up all the odd numbers, you just get the square. If you add up the first n odd numbers, you get the square of the nth number. So that's an easy way to figure out, well, the how to find the squares, just by adding up the odd numbers. 36. So let me look at problem 36. And so this is sort of the same thing. 6 plus 9 plus 12 plus 15. Okay, so let's add these up and see what we get. And so again, this is arithmetic because you keep adding the same amount to get to the next term. So I know that the sum of the first n terms of a arithmetic series is just 2a1 plus n minus 1d. In this particular case, the first term is 6. The common difference, well, to go from 6 to 9, add 3 plus, so 6 plus 3 is 9, plus 3 is 12, plus 3 is 15. So the common difference is 3. Let me multiply the 3 inside the parentheses. Oops. And so I get S of n is equal to n over 2. 12 plus 3n minus 3. Oops. So I get S of n is equal to n over 2 times 3n plus 9. Okay? And so if you add up so this is equal to, well, maybe I'll leave it like this. Let me factor out a 3, I guess. So this is 3 halves times factoring out 3 n plus 3. So if you add up 6 plus 9 plus 12 plus 15, and you add up the first n terms, you get 3n over 2 times n plus 3. Let me do problem number 38. Suppose that the sum of the first n terms is 55. The sum of the first 13 terms is 130. In exercises 37 through 40, find a formula for S sub n, the sum of the first n terms of an arithmetic series. Okay, so let's do that. I know that S sub n is equal to n over 2 times, well, a1 plus an. Actually, let's do it with the other formula. 2a1 plus n minus 1d. Okay, so let's first look when n is equal to 10. And so if I plug in 10, I get S sub 10 is equal to 10 over 2 times 2a1 plus 10 minus 1d. Well, S sub 10 is 55. 10 divided by 2 is 5. 2a1 plus 9d. Let me divide both sides of my equation by 5. So I get 2a1 plus 9d equals 11. Let me call that r sub 1. Next, let me look when n equals 13. So if I plug n equal 13 into this equation, I get S sub 13 equals 13 over 2, 2a1 plus n, 13 minus 1d. And so, well, S sub 13, they said, is 130 equals 13 over 2. 2a1 plus 13 minus 1 is 12d. Okay, so let me divide both sides of my equation by 13. Multiply by 1 over 13. So the 13's cancel. 2a1 divided by 2 is just a1. 12d divided by 2 is 6d. 130 divided by 13 is 10. So let's call that R2. Okay, so actually in this case I should have multiplied by, well, doesn't matter. Let me get rid of, I guess, the A1. So let's multiply by negative 2, R1. So we get a negative 2a1 minus 12d equals negative 20. And I have here, let's add to our 1, which is 2a1 plus 9d equals 11. So if I add these, I get a negative 3d equals negative 9. Divide both sides of my equation by negative 3. So I get that the common difference is just equal to a positive 3. Okay, good. And so from, well, let's say equation R2, I get that A1 plus 6D equals 10. So A1 plus 18 is 10. Subtract 18 from both sides. So A1 equals negative 8. And so I get that S of n. So now I know I can plug in here. I know A1 and D. So S of n equals n over 2, 2a1 plus n minus 1d. And so S over n is equal to n over 2. 2 times negative 8 is negative 16. Let me multiply the 3 inside the parentheses. Plus 3n minus 3. And so I get n over 2 times 3n minus 19. And so I get that if the sum of the first 10 terms is 55, the sum of the first 13 terms is 130, then the sum of the first n terms is going to be n over 2 times 3n minus 19. That was problem number 38. Let me do problem number 40. A sub 1 equals negative 4. S sub 15 equals 675. And let's find the sum of the first n terms. Okay, so let's do that. And so, having some technical difficulties here. Okay, and so S sub n is equal to n over 2 times 2a1 equals a1 plus an. Okay, so let's just use this formula. When n is 15, so n sub s of 15 equals 15 over 2 times, well, a1 plus an. Well, S of 15 I know is 675. A1 I know is negative 4. Actually, let's use this formula. Not that it really matters, but I like to use this formula. 2a1 plus n minus 1d. Let's use that formula instead, just to get the common ratio d. So this is 2a1 plus n minus 1d. So 2 times A1 is negative 4 plus 14D. Okay. And so I get 675 is equal to, I can just I can do this as 15 times. Well, 2 times negative 4 plus 14D, all divided by 2. So 675 equals 15 times negative 4 plus 7D. Divide both sides of the equation by 15. And so 675 divided by 15 is just 45. Equals negative 4 plus 7D. Add 4 to both sides of your equation. And so 49, oops. And so 49 equals 7D. Divide both sides of your equation by 7. So D is equal to 7. Okay, good. And so now I can figure out the general term here for the sum. So S sub n is equal to n over 2 times 2a1. But we know what a1 is. A1 is negative 4 plus n minus 1. D, and I know what D is. D is 7. We just calculated it. And so S sub n is equal to n over 2 times negative 8 plus, let me multiply the 7 inside the parentheses. So by the distributive property, 7n minus 7. And so finally I get that S sub n, the sum of the first n terms, is just n over 2 times 7n minus 15. And that is your answer. So given that the first term is negative 4 and the sum of the first 15 terms is 675, and the fact that this is an arithmetic series, we can find that the sum of the first n terms of this arithmetic series is n over 2 times the quantity 7n minus 15. Let me do problem number 42. Well, let me note, if you look in your book, they've actually given you some facts. So just note these facts about the properties of summation of the series. So note that the sum of, I don't know, let's say k equaling 1 to n is just equal to n. 1 plus 1 plus 1 plus 1 added up n times is just equal to n. Next, if you add up 1 plus 2 plus 3 plus dot dot dot, the first n elements, you get n plus 1 over 2. 3. If you add, and I guess I can start this anywhere, k going from k0 to n plus sum, let's start at the same place, bk, then this should equal the sum k equaling k0 to n of ak plus bk. So you can always just add the sum of two series is the series of their sum. And, oops, if you have, oh, let's say a constant times a sub k, by the distributive property, you can always bring the constant outside the summation. Of course, I don't need to start at 1. I could have started anywhere, but, oh, actually, I guess they wrote it as starting anywhere. Okay, question. Oh, this is just a distributive property. If you have, let me just write it out for two numbers. If you have a constant outside of the summation, you can always bring the constant inside the summation. It's a distributive property. It's just that instead of having two numbers, maybe I have a whole bunch more. Yeah. So this is just a distributive property, just written sort of in this sigma notation. Yeah, it makes right. It looks, yeah. So if you're not used to this sort of sigma notation, it just looks a little weirder. But yeah, no, this is just the distributive property. Okay, so let's do. Oh, let's say um, problem number 42. So problem number 42 says k equaling 1 to n of 6k equals 3n n plus 1. So it says use mathematical induction to prove the following. So let me first note that if I use the properties above, I could actually prove it. But they don't want me to do that. But let me just show you this first and then prove it by mathematical induction. So note that by this, I can just bring constants out in front of the summation, distributive property. And well, the sum k equaling 1 to n is just equal to n times n plus 1 over 2. 6 divided by 2 is 3. So this is equal to 3n n plus 1, which is what we wanted to show. But we don't want to show this. We want to prove this using mathematical induction. So let's prove this using mathematical induction. So let's do the initial case. So for the initial case, I want to show that this formula works when n is equal to 1. And so I want to show that if I replace n here by 1, I get the same result. So let's look. Is the sum k equaling 1 to 1 of 6k? Well, let's see. This is just equal to 6 times 1, and I just added up one time, so that's 6. Let's replace the right-hand side by 1. 3 times 1, 1 plus 1 equals 3 times 2, which is 6. So therefore, I've shown that the sum k equaling 1 to n of 6k is equal to 3n times n plus 1 when n is equal to 1. So I've shown that the initial case holds. Okay, good. So the initial case holds. Now I want to show that the induction case holds. So let's look at the induction case. So the induction hypothesis is that this formula works. Oh, I guess let's not use K. So let's say that sum K equaling 1 to N. Let's use a different N of 6K. Suppose that that is equal to 3N times N plus 1. Then I want to show that if we replace capital N by capital N plus 1, then the formula still works. So let's see. Well, let's look what happens when I do the next element. So this is equal to the sum of the first N of these plus the last one. Well, by the assumption, we have that the sum of the first N terms is just 3N times N plus 1. That N looks like a fancy N. It's just I can factor out an N plus 1. What remains is 3N. Actually, I can factor out a 3 also. So let's factor out a 3 and N plus 1. So that what remains is, well, N. 6 divided by 3 is 2. I can write N plus 2 as N plus 1 plus 1. 1 plus 1 is 2. Therefore, I'm done. So thus, I've shown that assuming that this formula is true for the nth term, then it is true for the n plus first term. So note that all I've done here is I've just replaced this n by n plus 1. So this n here becomes n plus 1. This n here became n plus 1. And so we've shown that the induction case holds. Therefore, by the principle of mathematical induction, sum k equaling 1 to n of 6k, is equal to 3n times n plus 1. So we're done. Let's do another one of these. Oh, which we've actually shown. Problem number 44. Sum k equaling 1 to n of 2k minus 1 equals n squared. We actually showed that. That's one of the problems we just did. There it is right there. We showed that the sum of the first and odd terms is just n squared. And that's all it's saying. Okay, so let's prove this by mathematical induction. So we showed it by actually calculating it. Let's actually prove this by mathematical induction. So let's look at the initial case. And so let's see. Let's do the sum k equaling 1 to, well, let's replace n by 1 for the initial case of 2k minus 1. Well, k is 1, so 2 times 1 minus 1. And I'm only adding one term, so that's it. 2 minus 1 is 1. When n is 1, 1 squared is, well, 1. So therefore, I've shown that the sum k equaling 1 to n of 2k minus 1 equals n squared when n equals 1. So that's the initial case. Let's do the induction case. Let's see if the induction case holds. So let's write down my induction hypothesis. So let's suppose that, oh, and I guess I'll use capital N again. Suppose the sum k equaling 1 to capital N of 2k minus 1 equals n squared. Okay, so then let's look what happens when I write out the first n plus 1 of these terms. Well, it's equal to the sum of the first n of these terms plus the n plus first term. So 2n plus 1. Oops, I'm using capital N. Capital N plus 1 minus 1. So this is equal to, well, by assumption, I've assumed that the sum of the first n terms is n squared plus, let me multiply the 2 inside the parentheses. So plus 2n plus 2 minus 1. So this becomes n squared plus 2n plus 1, which we can factor as n plus 1 squared. And so we've shown that the induction case works also. So therefore, so we have shown that, well, if I assume that the formula works for the sum of the first n terms, then it also works when we replace n by n plus 1. That this formula now is the same when I replace n by n plus 1. So, by the principle of mathematical induction, this formula works for every n. The sum k equaling 1 to n of 2k minus 1 is equal to n squared. And this is true for every natural number n. Okay? Here I'm assuming, obviously, n is any natural number n. I don't know, maybe I'll do one more. So that's 46. So let me do problem number 46. This is equal to n times 3n plus 1. Okay, so again, we've actually proven this, but let's prove this by mathematical induction. So let's look at the initial case. And so let's look at the sum, k equaling 1 to 1. So let's see if this formula works when n is equal to 1. Well, 6k minus 2. So we place k by 1. And since n here just ends at 1, well, there's only one term to add up. So 6 minus 2 is 4. And let's look at n times 3n plus 1 when n is equal to 1. Well, 3 times 1 is 3, plus 1 is 4. So these are equal. So therefore, I've shown that the sum k equaling 1 to n of 6k minus 2 is equal to n, 3n plus 1, when n equals 1. So I've shown that the initial case works. Let's do the induction case. Let's suppose that the sum of the first n terms, the formula works. And so let's suppose that this formula works for the nth term. Let's try to show that it works now for the n plus first term. So this is the same as the sum of the first n terms plus, well, maybe I should actually, let's give it some more room here. So this is equal to, I'll just give it some more additional room here, is equal to sum of the first n terms plus the n plus first term. Okay. Well, by assumption, the sum of the first n terms is just n, 3n plus 1. And let me multiply the 6 inside the parentheses. So by the distributive property, I have 6n plus 6 minus 2. And so let me multiply the n inside the parentheses. So I get 3n squared plus n plus 6n plus 6 minus 2 is 4. So this is 3n squared plus 7n plus 4. So I can factor. This factors into n plus 1 times 3n plus 4. So you get 3n squared plus 4n plus 3n is 7n plus 4. Let me write this as n plus 1 times 3 n plus 3 plus 1. So I can write 4 as 3 plus 1. So I can write 4 as 3 plus 1. And then I can group the 3n plus 3 together. And I can factor out the 3. So I get 3 times n plus 1 plus 1. So therefore, I've actually shown that the induction case holds. So I've shown that, so thus, I have shown that, well, if I assume that this works, the sum k equaling 1 to n of 6k minus 2 is equal to, well, we assume that it was equal to this, n times 3n plus 1. Then I get the sum k equaling 1 to n plus 1 of 6k minus 2 is equal to, well, notice I got n plus 1 times 3n plus 1 plus 1. So notice that if I replace this n by n plus 1, then the formula also works where I replace n by n plus 1. And let's see what the question is. Can you just say therefore? Therefore, oh, instead of thus? Sure, therefore, there. Thus, therefore, same thing. Oh, yeah, therefore, you can just say therefore. Therefore, yeah, you don't need to need to say the words I have shown. No, you don't need to say that. Therefore is sufficient. I just wrote out the extra words because sometimes people want to see those words. But no, you just have to say therefore. Okay. Okay. Uh, so the induction case holds. So thus, so therefore, but these words are necessary. Therefore, by the principle. So you have to write this out of mathematical induction. We have shown that, well, the sum k equaling 1 to n of 6k minus 2 equals n, 3n plus 1. And this holds for every natural number n. Okay, so that's probably, yeah, that's probably enough. So that really finishes off section 15.5. And I guess that's it for today, even though, yeah, I guess that's it for today.